Dear students, we are almost in the last phase of this chapter, Legendre's function, where in today's lecture I will discuss derivation of an important formula known as Rodrigue's formula of Legendre's function. That is the form of Rodrigue's formula. P n x equals to 1 upon 2 power n into factorial n into nth order derivative, that is dn by dxn, of x square minus 1 whole power n. What about analysis of this formula? It is providing us P n x, means Legendre's function. So it's nothing but an alternative form of Legendre's function. Let's talk over its derivation. We are starting with assuming that x square minus 1 whole power n equals to some new variable, say y. Then we differentiate it once with respect to x. We get dy by dx equals to, simple kind of differentiation, it's n into x square minus 1 power n minus 1. Then it's multiplied with differentiation of x square minus 1, which is 2x. So that is about the beginning of derivation. And in next step we are multiplying this equation by x square minus 1 both the sides. Why? What is the reason behind that? It's a simple reason. By doing that, that power of x square minus 1 n minus 1 now becomes x square minus 1 power n, and for which y can be replaced. So that right hand side becomes 2 into n into x into, that is equals to y, so 2nxy. That is named as equation 7.42. Now we will apply an important theorem of differentiation, which is known as Leibniz theorem. So we are differentiating that equation 7.42 with respect to x, and how many times? N plus 1 times. So that is about the facility provided by this theorem. We can differentiate a certain function with respect to a certain variable over a number of times. So in left hand side it's dn plus 1. Why? Because we are differentiating n plus 1 times. So dn plus 1 over that left hand side x square minus 1 into dy by dx is written as y1, just for simplicity. And in right hand side 2n is constant, multiplied with dn plus 1 over x into y. Let's talk over details of Leibniz rule, that how it's working here. Now it's a generalization of product rule. So it's written in that form. X square minus 1 is one factor multiplied with y1. So product rule of 2 is generalized here through Leibniz theorem as x square minus 1 remains invariant, that is first term remains invariant, or one of the factors remains invariant, and dn plus 1 is applied over the other factor, say y1, plus n plus 1 c1, because it's n plus 1 times differentiation, that's why it's coming there through Leibniz theorem. So n plus 1 c1, dn plus 1 y1 is decreased by one integer, so it's dny, and x square minus 1 is now replaced by its first order derivative, so d of x square minus 1, and that will be the story in continuous step. That is n plus 1 c1 is now replaced by n plus 1 c2 in next step, and dn y1 is decreased by integer 1 continuously, so dn minus 1 y1, and d of x square minus y is now increasing with one integer, so it's d square x square minus 1, and it can be added up to several more finite number of terms, but we are finishing it up to this. Why? Because it's d square x square minus 1, and if you differentiate x square minus 1 twice, you will get 2. and in next term it will be d cube of x square minus 1, that will be 0, and so on. All zeros will be obtained in remaining term. That's why we are stopping here in that left hand side. Now what about right hand side? It's 2 into n constant taken outside. Then dn plus 1 xy. Say x remains invariant, dn plus 1 over y plus n plus 1 c1 as usual. Then dn plus 1 y is decreased with one integer, so dny, and x is differentiated first time dx, and it's not extended up to several more terms. Why? Because in next term it will be d square x, then d cube x, all will become 0. So it's about applying Leibniz theorem. I hope you understand how you can apply that. Now we are writing all those terms with simple symbols like x square minus same, then dn plus 1 of y1, that n plus 1 is added in subscript of y, just for simplicity is reason, nothing else. So it's becoming y1 plus n plus 1 means yn plus 2 plus, what about that term, n plus 1 c1 means simple n plus 1, then dny1, add that subscript, that will become y n plus 1, as you can see there, it's yn plus 1 into d of x square minus 1 is 2x. Next term n plus 1 c2 means n plus 1 n upon 2, and it's not looking like that upon 2, because d square of x square minus 1 means 2 is cancelling that n plus 1 n upon 2 part. And what about dn minus 1 y, subscript 1 plus n minus 1 means it's n only, so y n. And same kind of symbols are utilized in right hand side, so it's 2n x, then it's yn plus 1 plus n plus 1 c1 means n plus 1, then it's yn, and dx is 1. And then we are simplifying that term, we are modifying that term, like x square minus 1 yn plus 2 is okay, then yn plus 1 is taken as common in these two terms, yn is taken as common in remaining two terms, and then it is simplified further to produce this particular step, and then yn plus 2 is again written in differentiation form, so dn plus 2y of upon dx n plus 2, then yn plus 1 means dn plus 1 y upon dx n plus 1, yn means simply dny upon dx n. It is written in detail again. Why? Because of a certain reason. Now we are introducing a new variable, say z equals to dny by dxn. So if it is z, then it will be dz by dx, it will be d2z by dx square. Hence the equation is reduced into this form, 1 minus x squared d2z by dx square minus 2x dz by dx plus n plus 1 into z equals to 0. Say equation 7.43, and the remaining part of the journey to reach up to that Rodrigue's formula will be continued in next slide. Now if you see that equation 7.43, last step or last equation of previous slide, if you clearly observe, it's a Legendre's differential equation, which we already discussed while deriving orthogonal property of Legendre's function in one of my previous lectures. And if that equation 7.43 is Legendre's differential equation, so Legendre's function p and x must satisfy that equation given with z as dependent variable. That means z must be in proportion with p and x, and if we take c as constant of proportionality, we get this equation z equals to c into p and x, and z means, as we know, dny by dxn equals to c p and x, and p and x means it's always equals to x. We have already discussed it in one of my previous lectures as Legendre's polynomial p and x is x. So if we substitute x equals to 1, then p and 1 will become 1. And in that case, that is only c equals to dny by dxn at x equals to 1. So we have to find value of c, and for the purpose, c as c is equals to that particular expression, we start with assuming y equals to x square minus 1 power n in different manner. We started with this equation We started derivation of Rodrigue's formula with this equation. I'm using this equation again, but now in a different manner. Factorizing x square minus 1 as x plus 1 into x minus 1. Power n is obviously over both these factors. And now I'm using that famous Leibniz theorem one more time over this equation. N times differentiating this equation, I get dny equals to dn of that right hand side with two factors, or two factors are multiplied there. So in left hand side is quite simple, dny upon dx n, and in right hand side I'm leaving x minus 1 whole power n, then dn x plus 1 whole power n is appearing, then it will be nc1, that will be decreased by one integer, so dn minus 1 x plus 1 whole power n, and d is appearing over x minus 1 whole power n, then nc2, that n minus 1 is decreasing by one more integer, so it has to be dn minus 2 over x plus 1. So please correct it. It has to be dn minus 2, make it 2, and then d square of x minus 1 whole power n, plus up to at last that d n x minus 1 whole power n will appear, and that will be free, so x plus 1 whole power n taken outside. Now I have to simplify this. X minus 1 whole power n is fine. If you differentiate x plus 1 whole power n times, you will get factorial n, plus nc1 x plus 1. Why x plus 1? It's coming from there. If you differentiate x plus 1 whole power n minus 1 times, you will get that. So you have to apply simple concepts of differentiation, you will get this step. And as we have to substitute x equals to 1, why? Because we obtained dny by dxn, and in order to find c, that value dny by dxn is to be evaluated at x equals to 1. So substituting x equals to 1 there, what will happen? X equals to 1 will make it 0. It will make next term 0. Before that last term, you will find that x minus 1 is an essential factor of all those terms except last term. It will appear in every term. So all terms at x equals to 1 will become 0 except the last term, and at x equals to 1 the last term becomes 1 plus 1, that is 2 power n into factorial n. So that is about value of dny by dxn at x equals to 1, means value of c. So c equals to 2 power n factorial n. And now that equation 7.44 is crucial for completing this derivation. Why? Now substituting that value of c there and dividing that value of c in left hand side, what will happen? Value of p and x, a formula for p and x is 1 upon c dny by dxn, and value of c is 2 power n into factorial n. So it's 1 upon 2 power n into factorial n into dn y by dxn is simplified as dn by dxn of y. Y means, as we know, x square minus 1 whole power n. So that is equation 7.4y, which is nothing but Rodrigue's formula. So that is about completion of derivation of Rodrigue's formula. In the next lecture, I will discuss practical part of Rodrigue's formula by virtue of one very important example, and that will be the last lecture for this chapter, Legendre's function.